All right. So for our afternoon session, this Dave Letterman show, my next guest needs no introduction. That's how I feel introducing Tara. She's actually from Boston, has gone to school here, then have been working at IBM and for 8 years at Google now. Many impactful work in speech recognition that came out in the last decade. Tara is one of the authors, so almost everyone knows her. She has been organizing many conferences, and listing all of that is going to take the whole time. So without further ado, let's hear from Tara.
Thanks, Arnab, and thanks for having me here. So I'm going to talk about end-to-end speech recognition, a multi-year research effort to, from research all the way to production with these models. This is a joint effort between the Google Brain, hardware, and speech teams. So let me begin by discussing what is end-to-end ASR. What we mean by this is a system where we take a sequence of input features and we map them directly to a sequence of graphemes or words with one neural network. And a system where we train that to optimize the final metric that we care about, which is word error rate, rather than optimizing individual components with separate objective functions. So let's look what I mean by that in more detail. So in speech recognition, we take our input speech, then we do some feature extraction to get log-mel features. In a conventional ASR system, these features are passed to an acoustic model, which maps features to a set of subword units. We then go to pronunciation model, which will tell us what sequence of subword units, typically phonemes, map to words. We then use a verbalizer to convert from spoken to written domain. And then a language model will tell us, probabilities of words following previous words. We compose the output of acoustic model with the pronunciation, verbalizer, and language model to get a sequence of candidate hypotheses, which we then might rescore with a second pass rescoring language model to get our final set of output words. This is how speech recognition was done for many, many, many years. And the system is very complicated. Each component is separately optimized. Typically, people have very deep knowledge or expertise in one of these. And what we did at Google in a multi-year research effort, and of course, many other research labs have done this as well, is to say, can we go replace this very complicated system by just one neural network, which goes from features all the way to words? And why would we want to do this? Well, one is just simplicity, but another is that we felt with joint optimization, rather than optimizing separate components, quality would actually be better. And another reason you'll see is that when we do this joint optimization with one network, it allows the model size to be much smaller. That gives us the ability to put a speech recognizer on the device. So let's look at the historical development of end-to-end ASR. One of the first methods was proposed by Alex Graves in 2006. This is known as CTC, Connectionist Temporal Classification. CTC introduces a special blank symbol B. So to compute the probability of Y are labels, given X are input features, we do this by maximizing the total probability of the label sequence here by marginalizing over all of the possible alignments. The main thing CTC helps us with is that no frame level alignment is needed. However, what you can notice in CTC is that each output is not dependent on the previous labels, so it's independent. And so this is a shortcoming of CTC that will show that typically, in order to get good performance with CTC, you need to incorporate some sort of a language model because you're not inherently doing it in the formulation itself. There's been a lot of work with CTC for end-to-end ASR. So Alex Graves and Navdeep Jaitley proposed character-based CTC to directly output word sequences given input speech. There was also work on incorporating LM into first pass decoding. And then people also looked at using CTC to train multiple languages. Longer span units, such as words instead of characters, were also looked at. And of course, there's been many, many others. But one of the main trends is that unless you're using long span units like words, CTC degraded significantly unless we included some sort of LM. So it was really hard to do end-to-end. In 2015, a few labs introduced this notion of attention-based encoder-decoder models as an alternative end-to-end model. And what this did was, you would first take your input features X, you would pass them through an encoder. You can think of this as a multi-layer recurrent neural network. This is very similar to an acoustic model. It would transform the input features into some higher level representation. We would then have an attention module, which would say, given these encoded frames, which features do I need to pay attention to in order to predict my current subword unit? This is very similar to the alignment model in a conventional system. Then we'd have a decoder, which is similar to the pronunciation and language model, which is an autoregressive neural recurrent network, which predicts the current subword unit at each token given the previous history. So you can see now with the attention-based models, it's not independent of the previous tokens you predict. You condition it on the previous token. So there's an inherent language model in here, which CTC doesn't have. In 2017, we did a comparison between CTC grapheme and attention-based models. Here, online means that the model is streaming, means it's a causal, it doesn't look to the right. And offline means that you have a full context model. And this is a word error rate on a voice search task. So the first thing that you can see is that the CTC grapheme model with no language model is significantly worse than the conventional model. And again, this is because of the conditional independence assumption in CTC. You can see the attention-based model, though it's offline, still lags behind the conventional model, but it's not that far off. And the 11.7 versus 8.6. So we got these results in 2017. And then we spent the next year or so really looking at how we can improve the attention-based model, even though it's offline, to sort of come closer to the quality of the conventional model. So that was our research in 2018 that I'm going to go through. How did we improve the attention-based models? The first thing we did is we looked at what we call multi-head attention. So as I said, attention tells when you predict a subword unit where you should pay attention to. So the plot here, this blue plot shows single head attention. And we thought usually multiple features should help predict what the current subword unit is, right? There should be some context around this. So we changed single head attention to use multi-head attention to look at different parts of the utterance to predict a label. And what you can see is that the model predominantly looks towards previous frames, but having that additional context helped a lot. We also looked at using longer subword units rather than graphemes. And why did we do this? One is typically longer units have a lower language model perplexity. So word units would have a much lower perplexity than graphemes. And also longer units improves the efficiency of the decoder because you have to update the decoder every time you output something. If you output a word piece as opposed to a word, it's almost 3 times less the number of units you have to output compared to grapheme. So we looked at using word pieces as a unit. And the reason we didn't go directly to words is in a search task at Google, the number of words is on the order of 4 million. It's very, very large. There's a very long tail to that distribution. And so we don't even have enough training data to model all the words. So word pieces seemed like a good choice. So when you train this word piece model, what you do is you take a bunch of text data, you train this to maximize the likelihood on the training data. And once you train it, it becomes position dependent and it's determined deterministically. So good afternoon, this is a tokenization into word pieces. And you can see this space here is position dependent. All word piece units have backoff units to characters, which means this model has no OOVs, which is what, if we went to word units, that would be a challenge for us. So typically end-to-end models, this is another change we made. Typically end-to-end models we train by optimizing what we call the cross-entropy loss. That is maximizing the likelihood of the training data given its history and the features. But that's really not the objective in speech recognition, right? The objective is word error rate. So we changed our loss function so that we minimize the expected number of word errors. So what we did is we would first train our model with the cross entropy loss. Once we got to a good point, we would then change our loss function such that we ran the model as a beam search, computed a candidate set of hypotheses Y here, and weighted them by the expected number of errors. And this more directly matches the metric that we care about in the end, which is word error rate. And the last thing we did is a few optimization improvements. So one thing is we use what we call scheduled sampling. So as I mentioned, when you train the model, you have to feed it the history of what you predict. When you're training, typically you would feed the ground truth history, but you could also feed the history from the model itself. So that generalizes better to test. To prevent overfitting, we also implemented something called label smoothing, which is you take the posterior, which is take the class that has a maximum probability, remove some fixed amount from it, and smooth it over the rest of the logits to prevent overfitting. And then we also use synchronous training for our gradient updates rather than asynchronous training. So if we put all of these improvements that I talked about together, word pieces, minimum word area training, multi-head attention, and the optimization, this is the latest model we had at the end of 2018. So the conventional model is 7.2 gigabytes if you count the total size of the acoustic pronunciation and language model. And the word area on this voice search task is 6.7. The attention-based model is 18 times smaller, 0.4 gigabytes, and its word area is 5.6. It's about 16% relative better than the conventional server model. So this was the first time that we had shown we could actually build such a model that could improve over the performance of a conventional model at a fraction of the size. But the main drawback of this model is it's not streaming. And streaming speech recognition is really important when we're talking about productionizing things. So that was our goal in 2019, 2020, how to take this EndtoEnd model and have it maintain this the quality that we just showed, but have it be streaming. And so I'm going to talk about the changes we made to have the model be streaming and how we deployed this to Pixel 4. Okay. So what is streaming recognition? Streaming recognition is I speak, and then I want to endpoint as quickly as possible. I want to close the microphone. I want to recognize the audio, send it to the server so that I can get a response back from the server as quickly as possible. This is really important for a good user experience. You don't want to speak and then have Google take 5 minutes to reply like, what's the weather today, right? It needs to be done very, very quickly. And this is critical to almost every product we launch in the speech team here, that it has to be streaming. So the attention-based model that I showed you is not streaming. It's offline. You have to see you compute the features for the entire utterance off the encoder and then say, where do I pay attention to? So we changed the EndtoEnd model to be what we call a recurrent neural network transducer. And this is very similar to CTC, with the difference now that you remove this conditional independence assumption. So what you do is you have an encoder, which is a set of recurrent layers like the acoustic model. You give it your acoustic features and it gives you some high-level representation. You have a prediction network, which is exactly like the decoder, which is again a recurrent language model. Then we have a joint network, which combines the acoustic and language predictions. The main difference is now at every step in the beam search, we take the label output and we feed it back to the prediction network. So that is where the dependence on the previous labels come, which is what CTC doesn't do. This whole thing is jointly optimized, so we don't need any alignment information. And the main thing is it operates streaming. So at every frame, we output either a output label token or we output blank, just like CTC. Only difference is you feed back the prediction to the prediction network. This gives us a streaming EndtoEnd model. As I mentioned, latency is very important for applications at Google. We want to close the microphone as soon as the user stops speaking. Typically, the way we close the microphone in the past is with an external voice activity detector that is trained to recognize speech and not speech. But in sort of going with the whole joint optimization approach, we felt that we could do this within the model itself. So to give you an idea, if I say, what's the weather in Boston? It's clear I have a complete thought. I'm done. We should be able to use not only acoustic information, but semantic information from what I said to know that I should close the microphone. I don't need to wait longer. So we can model that by folding the endpointer into the end-to-end model itself. So what we did is we had the model actually predict what we call an end of utterance token when we finish speaking, rather than making the endpointing decision just on acoustics alone. That allows us to make the decision on acoustic and semantic information. And of course, we did some optimization to try to make sure this end of token utterance is emitted as close to when the user stops speaking as possible. That you can, I've linked papers in these slides and you can see those. Okay, so now let's see why this end-to-end endpointer is so important. So the first experiment we did is we took an on-device RNNT model with a voice activity detector. That's that separate endpointer, which is trained on acoustics only, and compared to the jointly optimized RNNT endpointer where we predict end of utterance. And we report two numbers. One, of course, is the word error rate. And the second is what we call EOU latency. This is after the user stops speaking, how long did we wait to close the microphone? So the ultimate goal here is we want to make sure we have the lowest word error rate and the lowest latency. And what you can see is by jointly optimizing the endpointer with the RNNT model, we have a much better trade-off between word error rate and latency compared to doing this separate optimization. Okay, so we have streaming, we have good latency with an endpointer. But naturally, if you go to a streaming model, you're going to take a quality regression compared to if you had that full context attention-based model. So then we thought, how do we put that full context-based attention model into our network, but still have it abide by latency constraints, still have it be as quick as possible? And what we decided to do is to run an attention-based model in the second pass. So what you can imagine doing is you have a shared encoder, you run a first pass RNNT decoder, which is streaming. You then take the candidate set of hypotheses, you can cache the shared encoder outputs. So now you have the encoder outputs for the entire utterance because they were already computed in the first pass. You've already emitted something to the screen from RNNT. Then you can run this attention-based listen attend spell model as a rescorer, rescoring the first pass hypotheses. So what this does is it gives us the ability to run something quickly within real-time constraints, but get that quality benefit that we miss when we go to streaming. So what you can see here is this is the on-device RNNT EP at 6.8. And when you add the LAS rescorer, you get an additional 10+% improvement down to 6.1. Okay, so if we put all of this together, that conventional server model I showed you before, if you add in the second pass LM, we're at 87.2 gigabytes. This is a classic model in the cloud that if you've used Google speech recognition, this is for ENUS, this is what you're using. The word error at 6.6, the latency is 870. We took the streaming RNNT model with the second pass LAS rescorer. It's more than 400 times smaller. The word error rate is 6.1, it's much better. And you can see the latency is improved by 90 milliseconds. So by the end of 2020, we were able to develop a model which surpassed the performance of the conventional model in terms of quality, latency, and size. And this model was launched for Pixel 4 at the end of 2020. So here's a quote from The Verge. So you can ask the assistant to do things local to your phone, and they'll happen instantaneously. It's a lot faster, and you don't really need to rely on the server. Here's a few demos. So here's a dictation demo. So the video on the left is the model in the cloud, and the video on the right is the end-to-end model on the device. And you can see how much quicker the on-device model is. And I'm going to play a demo now. I'm not going to play all of it, but I will share the slides with you. And the demo is 10 minutes. I'll just play a little bit so you can see it. But this was presented at Google I/O a few years ago. And you can just see. Oh, here.
Hey, Google, open calendar, open calculator, open photos.
You can see how
Set a
quick it is.
timer for 10 minutes. What's the weather today? What about tomorrow? Show me John Legend on Twitter. Get a Lyft ride to my hotel. Turn the flashlight on. Turn it off. Take a selfie.
It keeps going. You guys can see it. Okay, so like I said, this model was released for Pixel 4 on device in the end of 2020. So up to this point, we developed an attention-based LAS model that had state-of-the-art performance, but wasn't streaming. And then we looked at this RNT end-to-end endpointer model, which is very fast and accurate, but is streaming. Combining both gives us a model which surpasses a conventional base model on the server, both in terms of quality and latency. One of the challenges we dealt with was, how do you deal with really long tail obscure phrases? Typically people use their phone when they speak to say, call so-and-so, really rare names. And this was something we worked on in 2021. How do we improve this further? So in Pixel 6, which was the goal for the end of 2021, we wanted to develop a model that not only surpassed conventional server-based model in terms of quality on general search traffic, but also long tail obscure phrases, because that's a main use case for Google. You don't want to use something if typically you'll say, call so-and-so, play this song. And if we can't get those words right, then it's not a good user experience. And that's a very critical component of the ASR system, getting these tail queries correct. We also wanted to make sure it was faster in terms of latency, both the endpointer and computational latency compared to our server model, and actually consumed lower power than the Pixel 4.5 model. So just to recap, the Pixel 4.5 model was this 2-pass system where we run a first pass RNNT, and then we run some second pass attention model rescorer. The main difference in Pixel 6 is the hardware changed. In Pixel 6, the Pixel 4.5 model, the model was running on the CPU. Now in Pixel 6, we actually had a on-device edge TPU that was 8 CPU cores and had either 8 gig or 12 gig of DRAM. So what this means is that you can run matrix multiplications super, super fast, but then transferring parameters from the CPU to the TPU is very, very expensive. So we wanted to make sure that we had an architecture where we can parallelize the encoder such that when we load it in, we can compute things super fast. In recurrent models, you have to wait for the previous prediction. We wanted to make sure we had a decoder small enough to fit in the SRAM. And we wanted to make sure that the second pass model was streaming to give us even better quality. And finally, we had a big effort to address the quality on long tail named entities. All right, so first let's look at how we improve latency by changing the encoder. So as I said, in Pixel 4.5, the encoder was an LSTM. And LSTM is sequentially dependent in time. So this means to predict any output at h of t, it is dependent on the current input and the previous inputs. So you can't parallelize this across time. Not only is this not TPU friendly, for really long form audio, let's say you want to do meeting transcription, you're going to see deletions because of the vanishing gradient problem, even with LSTMs. So with a conformer or transformer type of an architecture, this is a lot more TPU friendly. We can parallelize, there's no recurrency in the model, so we can parallelize the multiple outputs at the same time given the inputs. And this is also much more robust for long form. So that was the first change. We changed from LSTMs to conformers on the encoder. Another latency improvement was to just improve the decoder. So the Pixel 4.5 model, the LSTM decoder was 33 million parameters. And as I mentioned, a big bottleneck when you move to a TPU is this latency transfer between the CPU and the SRAM of the TPU. We wanted to make sure we had a decoder that was small enough to fit inside the SRAM, such that we can compute multiple outputs at the same time. So the SRAM, to give you an idea, is only 8 to 12 million parameters. So we had to make sure the decoder was small enough. So what we did is we explored if we could replace this big 33 million recurrent model with a simple lookup table. So you give a few previous predictions, compute the embeddings of this, and pass that directly to the joint layer. And actually that worked quite well. We were able to shrink it from 33 down to 2 million parameters with almost no loss in accuracy. So by going to the embedding decoder, we got about a 30% computational speed up with no accuracy degradation. Okay, the third was a quality improvement. So in Pixel 4.5, we had this notion of emit the first pass with RNNT and then rescore that with an attention-based model. First of all, this is not very ideal for long form because you segment multiple points in the utterance and then you have to rescore each of those independently. And typically beam search is better than rescoring. So we were trying to see if we could run a second pass beam search that looked ahead in time, just like the attention-based model, but we could run this in a streaming fashion. So we developed this model, which we call multi-rate encoder or cascaded encoder. There was 3 different papers that did this at Google. We looked at the last one that was developed by my colleague Arun. And so the way we do this is we run a first pass causal encoder that only looks to the left. That goes to the decoder and that emits the first pass hypotheses. We take the output of the causal encoder, then we run a non-causal encoder on top that looks just 1 second to the right. And then again goes to the same decoder and outputs the second pass. Because this is done on a TPU, even though we're delaying by 1 second, we can do that computation instantaneously. So there's not actually a 1 second delay when you see the results emitted to the screen. So what this does is it gives us that quality improvement so we can run the second pass as a beam search, but still do it in real time. And this is much more robust to long form compared to an attention-based rescorer. Okay, and lastly, to improve long tail named entities, we looked at using a neural language model. And one of the things we did was we introduced this was done by our colleague SANE, called the hybrid autoregressive transducer hat factorization. So typically when you do shallow fusion, you take the posterior from the EndtoEnd model P of y given x, and you interpolate that with the language model P of y. And that's not actually mathematically correct, right? And what we end up doing is we tune some internal language model weight. And so what he said is, instead of interpolating with P of y given x, I'm going to subtract out what we call an internal language model score, which is P of y internal to the model. So if you just look at this, P of y given x minus P of y from the same model would give you P of x given y. That gives you a generative model, which you can then interpolate with an external language model much more easily. And he showed in his paper that quantitatively, this is much better to incorporate an external LM compared to just doing the standard P of y given x plus an LM. So we used this hat factorization and looked at 2 different language models. The first is to incorporate what we call a contextual biasing FST. That is, let's say you have in your phone a set of contacts or a set of songs or a set of apps that you commonly say. You could represent that by an FST and bias your search towards that during your beam search. We also looked at training a conformer language model on 100 billion text utterances, which is a lot more than the 100 million utterances that our EndtoEnd models trained on, that's trained on audio text pairs. That allows us to capture the long tail better. And what we do is we take that and rescore the hypothesis after the second pass with this. Okay, so the first question is, how does this model compare on just general search traffic? The first column is the classic server word error rate. The second column is the LSTM Pixel 4.5. And the third column is conformer. And you can see this conformer cascade encoder plus neural LM is significantly better than classic or a Pixel 4.5 on every single test set. This is the best ASR system to date Google has built. And now let's look at long tail. So one way we do this is by looking at biasing test sets. So as I mentioned, biasing is an attempt to say, let's bake in some prior knowledge into the speech model about what I'm going to say. So if I know I'm in Boston, I'm going to ask questions about about restaurants and other geographic entities in Boston. Or I'm probably going to, when I say call or text, it's going to be somebody in my phone list or songs that I commonly play. So what you can see is this is the classic word array. The number in parentheses is without biasing, and the number outside the parentheses is with biasing. You can just pay attention to the first number. And these are three commonly used use cases: contacts, media, and apps. And again, what you see is that the Pixel 6 model is significantly better across all verticals compared to Pixel 4, 5, and server. And it's the best ASR we have built. Finally, when we launch any model, it's not just evaluating this test set, but it's also saying, can we take some live unseen data that the model has not seen? And can we run what we call a side-by-side? That is, we take the on-device model and a server-based model. We run it on the same logs data. We take the hypothesis. We take 500 utterances where the hypotheses differ between the two systems, and we send them to raters for comparison. A win here means that the end-to-end model won over the server-based model, loss is the other, and neutral means they're about the same. The p-value is basically how statistically significant these differences are, and impact is how much of the traffic do we impact. Typically, an impact greater than 1 e to the minus 2 is extremely significant. So you can see here that the win-loss ratio is 120 to 36, and impact is much larger than 1 e to the minus 2. So this tells us that this model is significantly better than the current server-based model. So here's one video that we put together on how we're fixing rare words. Let me play this now. So what you can see, I'll play it again, is that Ryan here is saying Bexar County, Texas. The model on the left is the Pixel 4 by model. Bexar County, Texas is actually spelled B-E-X-A-R. You can see the model on the left without the LM gets it wrong. Then the one with the LM will get it right. Let's see it again.
Bexar County, Texas.
Okay, and
Bexar.
I'm going to play a video from the Google I/O last year about Pixel 6. Again, this video is 10 minutes. I'll play a few minutes and you guys can watch more.
Let's talk about how Tensor is making typing much faster on Pixel. Obviously, speaking is the fastest and most natural way to go, but today's voice input systems just haven't been up to the task. First, understanding the nuance of human speech is really a hard problem, with challenges that are unique to each person. It means understanding syntax, intent, and the context of your request, knowing the terms and names that are important to you, but potentially uncommon to others, understanding your accent and dialect, isolating your voice when there's background noise, and even hearing you correctly if your mouth is full. Google has led the industry for years with our natural language processing. It's why search queries are so accurate. Google Translate is so good. Thanks to some outstanding work from our speech team, Pixel 6 has an on-device speech recognition model that can transcribe speech with incredible accuracy. And thanks to Tensor, it does it using half as much power as previously possible. It's the most advanced speech recognition model ever released by Google. With this new capability, we rethought the voice typing experience based on some key insights about how people write. Let me show you how it works. Hey, Ronnie, are you still up for dinner tomorrow? With our friends? You can see how accurate the transcription of my friend's name is. Pixel is smart enough to take the hint from my contacts list, and the mic stays open while I tap to insert a clarification about who's coming. Pixel even automatically adds the right punctuation, so I don't need to specify where to put commas and question marks. Let's keep going. I hope you can come. Catherine is hosting this week. Of course, Pixel won't always know which Catherine I'm talking about, and the one I have in mind spells her name with a K. The language model also helps with transcription suggestions, so corrections make sense based on what you're saying. Historically, transcription suggestions have been the same ones designed for typing based on keystroke proximity. But that doesn't make any sense if you aren't typing with keystrokes. Now Pixel's model is phonetically based, meaning it suggests corrections that sound similar. So Catherine with a C becomes Catherine with a K, instead of catharsis, cathedral, or whatever else you might have ended up with. And to make voice typing as fast as possible, I should be able to do more with my voice, including commands like clear or send. Pixel is smart enough to understand that I don't want those words in my message. I'm sure it's going to be great. Clear. I'm looking forward to it. Catherine has a really nice new place. Send. See how fast that was? Also notice that your phone remembered it's Catherine with a K, so you won't have to make the same edit twice. The model adapts to your usage. And watch this. The model also unlocks the accuracy of emoji transcriptions, which is so much faster than searching through little pages of icons. I think we're making homemade pasta emoji and ice cream emoji. Send. With the new speech model, typing with your voice is faster and easier than just typing with your fingers. Thanks to Tensor and these new breakthroughs, we can do all this on device without connecting to a server, so it's super fast and reliable. We really think it's going to change how you use your phone. Google's natural language understanding allows us to rethink phone calls too. Call screen is great for shielding you from spammers. Unknown callers have to say why they're much better for you. Hopefully, line and feature station. Improves Pixels can tell you about it.
I'm going to skip here so you guys can see this.
Nice info available recognition model. Google's ML research enables things like helpful voice typing, calling assistance, and translation on Pixel.
And is a huge star in the United States.
So this is showing how we can do live translate with the same model.
Thank you very much for being our first live translate interviewee.
私たちの最初のライブ翻訳インタビューであることに感謝します。
I love seeing what sparks joy in other people's lives. What sparks joy for Yuri?
私にとっては、一人でも多くの方がお片付けを終わらせて、ときめく人生を送っていただくこと。これが喜びです。For me, it's a pleasure for as many people as possible to finish cleaning up and lead a thrilling life.
So to summarize, this Pixel 6 work, over the past 4 or 5 years, we developed many iterations of this End-to-End model. The latest model is this Cascade encoder plus neural LM. It's the best model that Google has developed to date in both general search and long tail quality and latency. Now, of course, we don't stop working here. There's always some new fun thing. Here's just an example of one thing that our group is working on, of many. Everything I showed you up to this point is US English, and we strive to make the user experience more global and inclusive. And so one way to do this is to naturally extend this to build multi-dialect models. And of course, many groups in the research community have been doing this as well. So when you do a typical multi-dialect system, you have a separate acoustic, pronunciation, and language model, and then a separate rescorer as well. So now imagine trying to maintain 80 of these, which is how many languages we have at Google. That's really expensive. So let's, imagine it would be great if we just had one model where we trained all 80 languages on. Why would we want to do this? One is, this is a whole lot simpler. We believe that if we share data amongst all the languages, particularly for low resource languages, this should be better. The joint optimization with end-to-end should obviously help. And most importantly, this is a big infrastructure simplification. Imagine that the internationalization team has one model to train rather than 80. That would be great. Now, this is, of course, a research dream. There's a lot of challenges when it comes to production, but that's why our jobs are interesting. So I'm going to give you, a little bit of story about how this has progressed. And of course, this is very active research as we speak. So one of the first versions of this model we looked at is, can we train it on 7 English dialects, and how would it perform? And for the first version, we said, let's give the model information on what dialect is being spoken. And we're going to do this by giving information of a language ID. And we did some experiments. Should we pass that to the encoder? Should we pass that to the decoder? Should we pass that to both? So we ran this on 7 English dialects, which are very different in the amount of data they have. And what you can see here is the first row is a model trained on each individual English dialect. And the second 3 rows are when you pass knowledge of the language, the dialect being spoken into the encoder, into the decoder, or both, but you're training one model now. And what you can see is that if you just look at both, training one model and giving the model some notion of what language is being passed in is actually better than a baseline model trained on each individual language. That's fine. It's just 7 English dialects. So now let's see what happens when we scale this up. So now we're going to scale this up to 44 low resource languages. And what I've shown here is the difference in word error rate between one model trained on 44 languages compared to a model trained on each individual language. This is a relative word error rate difference, so here lower is better. And what you can see is if we compare this one model trained on 44 languages, it wins on 35 out of the 44. And again, we have given the model notion of what is being spoken. One of the benefits of this is you get cross-language sharing and the infrastructure is simplified. All right, now let's go from 44 and make it even bigger. Now let's go all the way to 85 languages. And again, I'm going to feed the model information of what is being spoken. One thing we found, which is not surprising, is that as you make this model bigger, as you add more languages, in order to maintain the quality compared to a model on each individual language, you have to make the model bigger, right? There's not enough capacity to train 85 languages with 120 million parameter model. So what this graph here shows is that as you make the model go all the way up to 1 billion parameters, as you increase the number of languages from 15 all the way to 66, you get good improvements. One of the things you have to keep in mind when you make the model bigger is you need to maintain quality across all the test sets. So what we notice is that if you just take a 1 billion parameter model and you train it from scratch, so this top line here is a model trained in each individual language. So this is US English, and then the average across 15 and 32 languages. If you just train this 1 billion parameter model from scratch, you can see you actually degrade. And part of that is because you're taking a degradation in the high resource languages. So what we did is we implemented this lifelong learning strategy where we first trained on 15 high resource languages, took that, initialized, and trained it to 32, initialized, and kept training to 66, and then 85. And with this lifelong learning strategy, we basically could develop a 1 billion parameter model that was as good as a monolingual model in each individual domain. And we have many applications that we're looking at exploring for this. So what are our research challenges? So we train on 85. Now, how do we scale this even larger? There's thousands of languages in the world. All of this work so far, we fed in a language ID. How can we maintain the quality when we don't feed in that language ID? Imagine you have a model on your phone. You can go to the Olympics, it'll transcribe whatever language it hears. That would be really cool. But that model has to be maintain quality when we don't have the language ID, when we need the model to fit on the device and can only be 200 million parameters, not 1 billion. So these are all open research challenges. And of course, code switching is also an interesting thing that once you stop feeding in a language ID, this gives us the ability to do. So these are all research challenges that we're looking at now. With that, I'll take questions.
Question?
Can you tell a slide about following up with offline recognition after online streaming recognition? I noticed if you are not quite reaching the low or the rate of the fully offline part, it's like 5.7 versus 6.1-ish. And I wonder if it's because you decoupled the encoder into the linear encoder and the additional encoder or the stick of the
No, it is because we coupled it. But if we trained it separately, we would get further improvements. But we had to couple it because of you have to cache the first pass outputs. Remember, like in our world, it's not just about quality, but we have to abide by all of these latency constraints, which makes it additionally difficult, and size constraints.
In general, when we are talking about multi-lingual, why would it'd be better to have one single model instead of having three different models for different languages, which is there is an additional overhead which comes by representing all the languages in one single model. Why would one single model be better as opposed to five?
Let's say you have a new research update, like a new research algorithm. So I showed you like whole research evolution from CTC all the way to, RNNT and beyond. Now you have to, we typically do research on US English. Now you have to deploy each of those models for 80 languages. For the internationalization team, that's a lot to train each of those, deploy each of those. If we could do it in fewer models, and there's a big simplicity argument. It makes the amount of effort to deploy such models much smaller. Now, of course, it comes with the concern that you have is, would you match quality, right? And that's what we have to check research-wise. But, we're getting to the point where, yes, we can match quality. If you look at the Mamazer 44, we can train on 44 languages and we can basically beat individual languages on most of them. Yeah, it's a research challenge. We had to see if it was possible. It seems like it is with enough capacity. This is a challenge. This is a research question for us. It's what keeps us busy. Yeah, so these models are all trained on server-based TPUs. There is an effort in the speech team on federated learning on doing training on the device. The big challenge with the training on the device is that it is too expensive to fully retrain a 120 million parameter model. So typically what they do is Google has some papers published in this space. KCHI, SIM, and others are the ones who have done this. They typically just adapt the joint layer. The joint layer is just a million parameters. Yeah.
So the long tail are those like current models, so they also produce something price versus coming to the concept. So
yeah, so all of the data that I showed you is k-anonymized so that it has to appear greater than 50 times in the training data. So there's all the legal ramifications are already sort of dealt with. Now, so the data we trained is k-anonymized to 50 and greater. There is another research effort that KCHI and team lead, which is how can you do personalization on the device where you say, very rare entities and you adapt the model. That kind of training has to be done only on the device. Yeah, that's not what we did here.
I think we should close because we're really late. Can I start questions during the coffee break? Maybe you're gonna still be around.
Yeah, I'll be around until like 4:30.
And so let's thank Tara again for this great talk.